Welcome to Hardfire. I'm Ronald WIECK. My guest tonight, and for the next two shows, is Ryan MACKEY, a research scientist at the NASA Jet Propulsion Laboratory, a specialist in vehicle autonomy and integrated systems health management for aircraft and spacecraft. This sounds very daunting, and in fact, one particularly desperate no-planer decided that he would transform MACKEY into a male nurse, not knowing what integrated systems health management is. That ploy was not successful. The reason we have Mr. MACKEY on, we're going to talk about the physics of 9/11. We're going to talk about not just the events from a political standpoint. In fact, we're going to stay away from the politics, and we're going to focus entirely on the science. 2006 was an interesting year for the self-styled truth movement. Its blogs and websites were full of hope. This was going to be the year that they exposed the vast conspiracy. They were going to prove that the attacks on the World Trade Center and on the Pentagon were an inside job. That didn't happen. It didn't happen in 2007 either, and it didn't happen in 2008. In fact, events caught up with the truth movement. Bush and Cheney are out of office, the Democrats are in control of both houses of Congress, and we have a new president who promises to undo virtually all of Bush's policies. Needless to say, the people promoting conspiracy theories are unfazed by reality. Reality is not their business. So this leads us to an interesting question. Some of us saw a plane hit the South Tower. We saw the plane crash into the building, and we understood that people on the plane died horribly. But there's a subset of the truth movement that believes there were no planes. And part of their argument hinges on the physics of the event. They claim that the plane would have simply bounced off the building. Now, most of us understand that this is nonsense. In fact, it's fantastic nonsense. It's lunacy. But could we explain why it's nonsense? Could we explain why the plane entered the building as it did? I couldn't, but my guest can. It's with great pleasure that I give you Ryan MACKEY, who will now tell us something about what he does.
I just want to say that I really appreciate your invitation, and I want to thank Gary Popkin and everybody else behind the scenes. This really is an unusual opportunity to educate and hopefully salvage something good out of what happened on that terrible day. If we could, I'd like to start first with a brief legal disclaimer, if you could put that on the screen. Ron, I'm sure you won't be surprised by this, but some of your viewers might be. At how many times I've been called a government agent or otherwise accused of doing this for money. But for the record, I want to be very clear. This is all done on my own time. This has nothing to do with my job. Nobody pays me a cent to do this, and you can read all the work I've done on this for free. I started doing this a few years ago because my understanding of the physics was also superficial. I understood in very gross terms what had happened, but there's a lot of detail there. There are a lot of opportunities to learn from that day, and there's a lot of information that's publicly available. I'd also like to do what I can to help others learn from it, and with any luck, people who have been snared by some of the crazier, unfortunate conspiracy ideas can break free of this with education. Also, just so this page isn't totally wasted, at the bottom there are 3 sites on the internet that explain a lot of the misconceptions held by the truth movement. So if you have a casual interest or you have some doubts, those 3 are a good place to start, and I highly recommend them.
Ryan, we're going to be dealing with science and not politics, but I wanted, while we're offering disclaimers, you will naturally be accused of being a shill for the military-industrial complex. I mean, I'm accused of things like that, and I don't know anything about physics. Is it not true that 9/11 really didn't spur any great development of new weapons programs? There was no sudden surge in military spending. I mean, you and your industry didn't benefit from the attacks of 9/11 in any tangible way.
That's really bigger than I can say, but I certainly haven't experienced that. That's not been my understanding. Certainly we've gotten embroiled in wars overseas, but that hasn't really led to a lot of new technology. And besides, I'm a civilian scientist. I have very little contact with the military. And none of my colleagues really saw any benefit from it at all. It was a great national tragedy, and the best we can do is understand it.
All right. So now, as I understand it, the focus of your lecture is on the physics of 9/11. Why the structures behaved as they did, why the aircraft behaved as they did.
Right. If we can go ahead to page 1-1, I give a brief overview motivating this discussion. One of the reasons to consider the physics is because, surprisingly, most of the arguments that come from the truth movement, both then and now, are or appear to be based in physics. They are not political in nature. For example, your explanation of the aircraft shouldn't have caused much damage to the structures on impact. That is basically a physical claim. It's not a political claim. Some other common claims are that the structures should have collapsed much slower than they did, or that they shouldn't have collapsed at all. And these are all things that relate to physics and science. So how do we answer these kind of questions? Most of us can't really afford to test an aircraft collision. That's an extremely expensive undertaking. But we can, on our own, come up with simple models with just a high school level of understanding, or talk to college professors or anybody who understands the subject. We can come up with these models and use it to answer whether or not these events make sense, and whether or not the claims that are coming from the truth movement are plausible. This is a real process the scientists actually use. Sometimes we call it a thought experiment, or a Gedanken experiment is found in quantum mechanics. Engineers use back-of-the-envelope calculations, rough order of magnitude calculations, and that's what I'd like to walk us through. So when you're ready, let's go to page 1-2 and start it off. So the question that I'd like to start with and do for this show is the basic question: can an aircraft penetrate a steel frame structure? So out here I've outlined a basic process for us to follow. We start by asking, has it happened before? And did anything similar happen before? Now that doesn't necessarily mean that nothing that happens is ever new, but nonetheless there are some similar examples in history, and we'd like to understand them. Let's identify what is important about the problem, what parameters, what quantities, what properties of materials and velocity and such matter to the problem. Let's come up with a simple model, and let's test it. And when we're done with that, let's see how our model stacks up to what other people are saying. And then we'll know if this makes sense or not. So let's go ahead to 1-3. I apologize, I'm going to run through this a little fast. But these slides are going to be available on the internet for people to review at their own speed with some additional commentary. But go ahead and stop me if I'm going too fast.
Ryan, could I interrupt just for one moment? Could you briefly explain to the audience how a scientist uses a model? In other words, we often hear conspiracists complain about a lack of physical evidence. Obviously, 8 years down the road, the rubble has been cleared away. There are no steel girders. The airplane debris has been cleared away. Why do scientists rely so heavily on computer simulations and other forms of modeling?
Yeah, that's a good question. The reason we rely so heavily on models is because the principal tenet of science is repeatability. If you can make something happen predictably over and over again, then you really understand the phenomenon you have under study. So what a model is, it's a simplified, practical way to replicate what happened in real life, or something you think might happen in real life. A model can be physical, it can be a construction that you build yourself and test it some way, or you can do a computer model, which is a simulation. You can do a mathematical model. A number of papers that have been written by real scientists on September 11th are mathematical in nature. All of these qualify as models, and the value to science is it gives you a way to repeat a phenomenon predictably when you need it to, so that you can study it. So if that's clear, let's go ahead to 1-3. The first thing we do is we look at some historical examples. Now, we know that sometimes when an aircraft hits a structure, it doesn't do that much damage. There were two examples from 2002 that did very little damage. One was the Pirelli Tower in Milan, Italy, and the other one was the Bank of America impact in Tampa, Florida. Both of these did not destroy the structures. They caused local fires, local damage, but that was it. Now, one thing to note though, both of these were light civilian aircraft that were both at fairly low speed. One of those two was accidental, but the other one was thought to be deliberate by a fairly young pilot, in fact. So we know that sometimes they don't do much damage. But if we go ahead to 1-4, there are also a couple of examples of impacts that do a lot of damage. The one on the left is a controlled test. So this is a model. This is a mock-up of an aircraft collision against a very strong structure. This was meant to test construction methods for nuclear reactors and was traveling much faster. It's a heavier aircraft. This was an F-4 Phantom test. The picture on the right is historical. This is not contrived. This is a real-world event. And what you're looking at is the deck of the USS Franklin. And in this case, the aircraft penetrated the deck, which had a light steel plating on it. It was solid wood, had solid steel girders underneath it. You can see some of the damage there. And this one was actually a fairly light aircraft. This was a mostly wooden World War II fighter plane of the day, either a Zeke or a Judy, and thought to be on the order of 300 miles per hour. So we know that some impacts do only a little bit of damage, but some do a lot more.
Now, this is something that always bothers me. We see the picture of a light wooden fighter plane penetrating a steel deck of an aircraft carrier, and yet there are people who will contend with a straight face that a commercial airliner weighing tens of thousands of tons can't break through a mostly glass facade of a building.
Yeah, that's right. Now, there are some details that are important here. It was a light wooden aircraft, but it did still have a metal engine. It was thought to be carrying a bomb at the time of impact, which has greater penetration ability. The deck of an aircraft carrier in those days is not as heavily armored as you might think. But what this tells you is it's not enough to just look at a picture and say this situation is just like that one. What it tells you is you need to put numbers on the problem. You need to really think about this quantitatively instead of qualitatively. And that's what we're going to do in this example. So let's go ahead to 1-5. When we think about our model, we need to think about what properties are important. Now, some people think, as you've heard, the aircraft should not have done any damage because steel is harder than aluminum, so the aircraft wasn't hard enough to do any damage, or the structure is much stronger than the airplane. But there are plenty of examples of cases where something that isn't strong and isn't hard does damage to something much stronger and harder than itself. You folks in New York recently witnessed a almost miraculous incident. The aircraft that went down on the Hudson was brought down by Canadian geese, which are quite a bit weaker and quite a bit softer than the titanium and superalloy blades in the engines. Unfortunately, everybody survived. But this has been known for a long time. People who design aircraft know that it is things like speed and momentum that make all the difference. What we've got a picture of down here is the canopy of an F-16 undergoing testing. And they test these things by firing chickens at them at up to about 450 knots. This is your average 4-pound frying chicken. It's much weaker, it's much softer. It's hitting an object that is designed to stand up to 20-millimeter cannon fire, and nonetheless, it can do substantial damage to it. So hardness and strength might play some role in a problem, but it's certainly not the only thing. So let's go ahead to 1-6. Here's another famous example. This is a window taken from the Space Shuttle Challenger. The damage you see here was caused by a single flake of paint. Now, this is a window that is very strong, pressurized in space, survives re-entry. Nonetheless, you put a crack in it with a speck of paint you can hardly see. So what this means is if you get something that's either heavy enough or fast enough, it can do grossly disproportionate damage to another object. A lot of people use the argument here and also in the collapse theories that an object can't do more damage than it itself has mass. It can't do more damage. It can't damage an object that's larger than itself. That simply isn't true if you get enough speed or enough force behind it. So let's go on to 1-7. We talk about strength all the time, but I need to provide a little background here because strength is more complicated than it may appear. Strength defines the actual force or the actual stress it takes to break an object. So if I take something like a bar of steel and I push on it on both ends with a force F, what's going to happen is that bar is going to compress a little bit. There's a little bit of springiness to it. So what I'm doing is I'm applying a pressure. That force divided by area defines a pressure. Now, if you look inside the bar while I'm doing this, every little piece of it is squishing by more or less the same amount. So what's going on is inside the bar is feeling something we call stress. The stress is like a pressure. It has units of force divided by area. And what we also define is something called the maximum stress. That's as much squish as it can possibly take, at which point it ruptures. The stress also gives rise to a quantity we call strain. Now, strain is the actual amount that it squishes. It has no units. It's like a percentage. So if I put a force on something and it squishes by 1%, so it's 1% shorter than it was to begin with, that's what we call 1% strain. So stress and strain are important to understanding the way these things behave. And let's go ahead to 1-8. There is a little bit of math in this presentation. I apologize for it. We're going to go through it very quickly. If we talk about an impact, something hitting something else, there are two quantities that are most important. One of them is pressure. And we all understand pressure reasonably well. It's a force divided by area. The other one, which is less well understood, is impulse. Now, what impulse is, it describes the total change in momentum caused by the impact. There's equations here. What I want you to look at is the bottom right, where we define what impulse is. Impulse is either force times the length of time these things are in contact, or it's equal to mass times the change of velocity of the object. Either of those works, and both of those are the same, and they're the same as a consequence of Newton's second law. Now, in an impact, to do damage, you need both of those. If your pressure is too low, you won't cause any damage. If your impulse is too low, you won't cause any damage. So what kind of impact are we dealing with an aircraft collision? Let's go ahead to 1-9. And here's our model. It's a very simple model. We can't understand easily all the contribution from the aircraft structure, how strong the aluminum is, how strong all the different rivets and things are. Let's just talk about the fuel to begin with. Let's talk about the easiest case of impact. So if I have a big block of fuel that's moving at some velocity v, and I'm going to hit a big column, can I work out what the pressure and the impulse are in that kind of collision? And yes, we can. I'm going pretty fast here. Let me go ahead to 1-10, and I want to cut to the chase. This is all the equations we're going to use, and they're very simple. What we're doing is we want to estimate the total amount of impulse. We want to estimate the pressure. Once we have those, we can look up on a table to see if that's enough pressure and impulse to destroy a column. The way you compute the impulse is equal to the mass times the change in velocity. Well, I know the mass of the fuel. It's just equal to the density of the fuel times the size. I know the velocity change because it starts off at the aircraft velocity, and when it's done hitting the column, it's stopped. So the change in velocity is just v. So that's what that first equation is. That's how you compute the total impulse. Now to get the pressure, the way you do that is you go back to a force. You use the fact that the impulse is also equal to the force times the length of time. So what is that length of time? The length of time is the amount of time it takes for that whole block of fuel to start touching the column until it's all moved and it's all hit the column. So that is equal to the length of the fuel block divided by its velocity, and that gives us the time. So from those simple estimates, we can come up with an expression for impulse, which is equal to the mass times velocity. We can come up with an expression for the pressure, which is equal to the density of the fuel times the velocity squared. And that's it. That's our simple model. We're done. This is good enough for us to start asking simple questions about what happened. So let's go ahead to 1-11, and let's put some numbers into it. These numbers are all things that you can look up. The density of fuel is well understood. I forget exactly what it is, about 80% that of water. The size of the fuel tanks, you can find these in the NIST reports. They have some drawings, and here's one of them that give you the approximate size and shape of the fuel tanks. You plug those in, what you find is for the slower impact, that's American 11, the pressure is 4,600 psi. The impact for the faster aircraft, United 175, is 6,800 psi. Now this immediately should start you thinking, that's a lot of pressure. that potentially is enough to go straight through a steel column. This is many, many, many times higher than it is here at atmospheric pressure at the surface. The impulse, again, this is a less familiar unit, so this number may not mean so much to you, but the lower impulse comes out to be about 16,000 pound-seconds. Now that is approximately the momentum of a 4,000 pound car going 80 miles per hour. So that's how much momentum is being transferred into a column during the impact just by the fuel. So that's a lot. Let's go to 1-12 and see how this stacks up. Can you see that chart, Ron?
Ryan, we're down to our last 5 minutes now. Obviously, this is a critical point in your lecture, so I think we're going to resume this in the second show. You did, in one of the slides, allude to Newton's second law. Mm-hmm. Now, I bring this up because so many conspiracists misrepresent Newton's second law. Tell us briefly what they're getting wrong, what Newton's second law actually tells us.
Yeah, Newton's second law is the one that describes motion. You apply force. What it says is that the force is equal to the rate of change of momentum. And usually people simplify this. If mass is constant, then the rate of change of momentum is simply mass times acceleration. So if you have an object in free space and you apply force to it, that tells you how fast it accelerates under that force. I've seen it misused by the truth movement a number of interesting ways. The most common and the strangest that I can think of is what we call the net force equals zero bunch. If you ever see this in an internet discussion, this is something we've run across a number of times. A number of people will claim that for any given object, the forces are all going to balance. This isn't Newton's second law. These are the other laws, that for every force there's an equal and opposite force. Well, that's not really true. If you have an object that isn't moving, Newton's second law says because it isn't moving, the acceleration is equal to zero. Or if it's traveling at a fixed velocity, the acceleration is equal to zero. So whatever forces are acting on it at that time do cancel out. Think of an object in free fall that has reached its terminal velocity. There's gravity and there's wind resistance, and those must be in balance because it's not accelerating. But these are very simple concepts, and if this isn't clear, I encourage you to talk to a college professor. Anybody well-versed in the subject will help you with it.
Well, that's an interesting point. Morgan Reynolds, who was chief economist for the Treasury Department in Bush's first term, is the guru of the no-planers. I have asked him repeatedly to run his theories by a physics professor, and he simply refuses to do it. There is a reason why he refuses to do it, because that would put paid to these rather bizarre notions. This is a problem with the truth movement in general. I mean, many truthers will decry the no-planers as disinformation agents. There are no disinformation agents. There are simply crackpots who disagree with other crackpots. But most of the people making outlandish claims are unwilling to subject those claims to serious scrutiny. Is there anything that you've said so far that another scientist would regard as in any way controversial?
You know, there's one good way to find out, and that is to ask other scientists, and I encourage it. Science, the process demands it. It demands peer review. It's quite possible that I make a mistake. It's possible that even in the presentation I put out so far I've made a mistake. So if there are
where could that mistake arise?
It could arise from anywhere. It could arise because I have a preconceived notion of the way things should work. So I set up a problem in a certain way. I could ignore a certain effect. I could do the math wrong. I could look at a bad source for some of my values. But the thing that's important is that I'm showing you all of the work. I'm showing you all of my assumptions very carefully so that you can go back and figure out exactly what is I'm saying. And you can satisfy yourself whether or not I'm telling the truth.
So simply put, the truth movement, to refute you, can deal with the tangible work that you've shown. They can try to show that your equations are wrong, that you've derived them improperly, that you've made computational errors. They could do that, but they won't.
Now, it is true.
Remember that the model we talked about here is a very, very simple one. There's a lot more detail to it. And this is why it's important to compare your model to what other people are doing. If you find that your model gives you a wrong answer or an answer that doesn't make sense to you, it's a good idea to look at your assumptions and think, well, gee, maybe there is a simplification that I shouldn't have done.
Ryan, we're going to pick up the next show right where we left off. And I can't thank you enough for being our guest. We have a lot more to come. I hope that the audience is finding this discussion as enlightening as I am. We'll be back. 2 more shows with Ryan Mackey. Thank you so much for joining us. See you next time on Hardfire.
Yeah, my pleasure.
This work is copyright 2008 by Ryan Mackey. All rights reserved. All opinions are those of the author alone and do not represent any agency, public or private. Photographs are used in accordance with fair use guidelines and may be subject to their own copyright protection. The author can be contacted at rmackey_email@earthlink.net. Additional online resources: 9/11 Myths, www.911myths.com. Mark Roberts Collection, WTC7lies.googlepages.com. 9/11 Guide, 911guide.googlepages.com. Hardfire is funded in part by the Libertarian Party of New York. www.ny.lp.org